Okay, last chapter, we learned all about the Bohr model, the quantum mechanical model, which is superior, and we didn't learn that much about it, but we learned that there's principal quantum numbers. N can start from 1, go up from there. We learned about subshells, S, P, D, and F, which describe different shapes. And each of those individual shapes, the sphere, the dumbbells, the double dumbbells, and the dumbbell with the donut, and then the F orbitals that we didn't look at, each of those individual shapes in their various orientations describes an orbital. And each of those orbitals can contain up to 2 electrons in it. We learned about where our S, P, D blocks are, our S being our far left 2 columns or groups, our P being the far right 6 groups, the rest of our main group, D being our transition metal block, and the F is the lanthanides and actinides, which we don't need to know. We learned about that. We learned about how to figure out the electron configuration, and we used the electron configuration to figure out the number of valence electrons. That's the outermost electrons, and it's just equal to the group number, the A designation. So 1A, 2A, 3A, 4A, 5A being group 15, as we see it on the periodic table in class. And then we learned how to put them together to form molecules or ionic compounds. And then we learned that there's a thing called electronegativity. And electronegativity, our highest value is arbitrarily assigned to fluorine, not really arbitrarily, but it gets a value of 4.0, and everything that's left and down has a decreasing amount of electronegative strength, or electron pull, electron riz, if you will, an attractive force. The attractive force that we're talking about, though, today is going to be built out of that electronegativity principle. So the electronegativity can cause slight positive and negative parts in our molecules. And we learned about how things can be polar if they have polar bonds, if our electronegativity difference is big enough, or they can be ionic. And so we can have polar and nonpolar molecules, polar things being like water, it has permanent dipoles. Nonpolar things being like hydrocarbons, things like methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane. That's probably enough anes. But things that look kind of oily, or things that behave like oils. And now we're building a little bit more out of that. That's why I bothered going through all of that rant and rave about description. So individually, those molecules can have polar, nonpolar, ionic. They can have those sort of properties. But they can also interact with other molecules. And in fact, they do interact with other molecules. And so since they're between molecules and they are forces, they are intermolecular forces, forces that exist between molecules, interactions that exist between molecules. So our intermolecular forces are attractive forces that exist between molecules. That's the inter part, not intra. Intra is inside, inter is between. So these are forces that exist between molecules. Intermolecular forces, I've got a fun double space there, are essential for many physiological processes. They're all over the place. Intermolecular forces are part of the reason that chemicals like, what's the name of it? I can't remember the name of it. But benzene, there it is. Benzene is a carcinogen. It's a chemical that you're not going to encounter in our lab, but is common, and it's sometimes found in aerosol products. There's a recall for some instant hair shampoo, something like that, because it had trace levels of benzene in it. Sometimes sunscreen gets recalled for it. And that's the reason that it's part of the reason that benzene is a carcinogen, because of the intermolecular forces that it has and its shape and other stuff. There's also less specific forces that exist between all molecules and atoms. So what we learned about the kinetic molecular theory, the idea that gases, oh, this was 2 chapters ago, sorry. Gases was the last chapter. We learned in kinetic molecular theory that our atoms and molecules just bounce off of each other perfectly, elastically. They don't lose any energy. There's not any interactions between them. That's not true in the real world. There are intermolecular forces that exist between all molecules and atoms. We'll learn what that force, that one main force is, and some of the other intermolecular forces as well. The reason that we can have things like liquids and solids, which we're largely made up of, there's also some hot gas, the existence of those is because of intermolecular forces. So we're going to be learning 4 intermolecular forces. They are electrostatic, electro like electricity, static, they're just always there, forces of attraction that exist between molecules. The strength of the intermolecular forces determines the state, solids having the strongest, liquids having the mediumest, and gas having the weakest intermolecular forces. The strength of those forces determines the state of the substance at a given temperature. Here it says room temperature, but any temperature kind of governed by how sticky the molecules are. That's what intermolecular forces are, basically how well do the molecules stick together, how well do the particles stick together. If they stick together really well, then it's really hard to separate them. If they're super glued together, it's going to be really hard to separate them. You'll need to put in a lot of energy, pour in a lot of heat to get those molecules to separate. The strong intermolecular forces tend to result in liquids and solids. Weak intermolecular forces tend to result in gases. Gases are not very stuck together at all. Part of our kinetic molecular theory was that there was empty space in between them. So completely separated molecules, they must not be very sticky because they're colliding with each other all the time, and they seem to not like to be around each other. Our first intermolecular force is the dispersion force, also called the London force, also called the London dispersion force. This is our first intermolecular force that we're going to learn about. Dispersion forces are caused by fluctuations in electron distribution. Electrons randomly distribute themselves. So if we think about an s orbital, just a sphere, that's what we'll be thinking about when we're thinking about dispersion forces. We'll just think about a sphere of electrons. The electrons are probably found somewhere within that sphere, and they might be in the p or d orbitals, and then they'll be in different shapes or whatever. But generally, we can think of our electrons being in a sphere. But just in that volume of the sphere, an area here not referring to two-dimensional plane, but just referring to like a general vicinity. They're generally going to be found in a sphere around the nucleus. And what can happen is that the electron distribution system can go wonky for a brief period of time. So in my mind, electrons just kind of teleport willy-nilly around within this sphere of the what would be described as an atom or a molecule. They're just randomly one place or another. And in helium, we've got 2 electrons. That's why we're using helium as an example. And so they can randomly just jump and be on one side, and then randomly the next moment they'll be back to normal. And these are instantaneous dipoles, so these exist for, think of the shortest time span that you can imagine, maybe the blink of an eye, and then shorten it, and shorten it, and shorten it, and continue shortening it until it's the smallest tiny little sliver of time. That's how long these instantaneous dipoles exist. They're there, and then they're gone, and then they're there, and then they're there, and they're gone, and they're gone, and they're gone, and they're gone, and they're there, and then they're there, and then they're gone. That sort of a thing. So it's completely random. It's kind of like the universe flipping a coin, except it's a really fast coin, and it's flipping at 10 100 billion times a second. So when these instantaneous dipoles form, we can get small partial positive sides where the electrons are not, and a slight negative on the other side. So within our nucleus, or within our atom, the nucleus is where all of our protons are. We also maybe have some neutrons there, but all of our positive charge is going to be housed in the nucleus. And a property that you might not be aware of with magnets is that positives and negatives can cancel each other out. The same thing works with protons and electrons. So if our electrons are well distributed around our nucleus, then they're effectively canceling out the positive charge that's on the nucleus. If they're both over to one side, though, they are more than canceling out the positive charge, but just on that side, because that's where they are. And then on the other side, our nucleus is completely unshielded. There are no electrons over there, or there's fewer electrons over there, maybe. And so that positive charge from the nucleus can get through. And that can influence its neighbor. It can be an influence on its neighbor and can pull over the electrons from a neighboring helium atom. And this exists for the shortest time span that you can possibly imagine. It's also incredibly weak. So the nucleus attracts the electrons next door. This is the key, this is the basis for what forms the dispersion force, or the London force, or the London dispersion force. This is just saying what I was talking about earlier, so we'll skip that. This is saying mostly the same stuff that I said before. The dipoles responsible for the dispersion force are transient, meaning they're there and gone. It's like somebody flicking on a light switch on and off as fast as they can. It's kind of, the forces are on, they're off, they're on, they're off, they're on, they're off. They're really fast. The magnitude, the size with a Z, size of the dispersion force, the strength of the dispersion force depends on a couple of things. How easily the electrons can polarize, how easily they can be pulled/move, if there's an instantaneous dipole next to them, so how influenceable are the electrons? And that depends on the size of the electron cloud. Because a bigger cloud, if we think of adding layers on, the more layers that we add onto our electron cloud, the bigger our overall area that or volume that our electrons can be in. And if they're further away from our nucleus is our positively charged center, if they're further from that nucleus, then they're going to be easier to influence. They're less strongly tied to that nucleus. They're less strongly influenced by the nucleus. So our takeaway, a larger electron cloud is more easily polarized. So one way that we can compare dispersion forces, because we like to look at trends, one way that we can compare or make a trend is by looking at molar mass. Molar mass can be used as a guide when comparing similar elements or compounds. So if we're in a group, in a column on our periodic table, then we can compare based on molar mass. because the things that have larger molar mass are going to have more electrons. We can also compare within a group of compounds. So the hydrocarbons would be one such group of compounds. That's all of those things that ended in ane that I was listing off. That was the first 12 hydrocarbons, things that are just hydrogen and carbon. So let's take a look at the effect of differences in dispersion forces for our noble gases. So we've got our noble gases, and we're looking at boiling point. Because they're gases, they're going to exist primarily as gases, and they're going to have boiling points. We can't compare melting points because I think you can't get solid helium. So boiling point works because helium does have a boiling point. So looking at our noble gases, these are in order that we would see them on the periodic table. We've got their molar masses pulled out, and we've got the boiling points looked up, found on a table somewhere on the internet. So looking at our molar masses, they increase as we go down. It's not a surprise, they're getting bigger. Their boiling points also increase as we go down. Notice that these are in units of Kelvin. So helium's boiling point is 4 Kelvin. That's 4 degrees above, or 4 Kelvin above absolute zero, when everything would theoretically be solids. This is an incredibly low boiling point. You have probably never witnessed or experienced 4 Kelvin. I have never experienced or witnessed 4 Kelvin, and there's a very good chance that none of us ever will for the rest of our lives. It's very rare unless you work in a space that specifically uses liquid helium, which is not most places. And then neon, argon, krypton, and xenon have increasingly higher boiling points. Xenon's boiling point is minus 110 Celsius-ish, which is also crazy, crazy cold. So increasing boiling point as molar mass increases. That's the trend that we're seeing here. Boiling point describes the temperature that the molecules separate from a liquid where they're touchingly close but they can move past each other into a gas where they are no longer touchingly close. So we're overcoming that last little bit of attractive force, that last little bit of stickiness between the atoms in this case, and completely separating them. The higher the temperature, the more energy they're going to have. Everything is kind of shaking a little bit, not because they're scared, not in their boots, just regular shaking, quaking, moving. And so as that temperature continues to increase, they get more energy to vibrate, and at some point, the boiling point, they get enough energy that they can completely separate. So what we're seeing with increasing boiling point means that we have more energy required to separate the atoms. And more energy required to separate atoms means that they are stickier. As I like to think of it. So they're stickier, little quotation marks there, which means that they have stronger intermolecular forces. And I'm going to abbreviate intermolecular forces as IMF. Don't get it confused for the International Monetary Fund. Which is also IMF. All right, hydrocarbons. I've already told you about hydrocarbons. They're a class of chemical containing only carbon and hydrogen. It's in their name, hydro for hydrogen, carbon for carbon. Which hydrocarbon? So we're thinking in the class of chemicals, in a family, in a class. Which hydrocarbon, C2H6 or C4H10, has the higher boiling point? Think about it for a bit. Would anyone like to make a guess about which hydrocarbon, C2H6 or C4H10, has the higher boiling point? What did we say on the previous slide causes higher boiling point? Okay. Somebody said something and I have no clue what was said.
Molar mass.
Molar mass. Molar mass, yes. That's what we're looking at in terms of the trend, and that certainly applies here. There's a couple of steps in between. But yes, that's what we would be looking at to make our decision. So C4H10, higher molar mass. Stronger intermolecular forces. And I'm not going to write out the whole thing. Well, we'll write it out once. Intermolecular forces. And then I can be proper and put IMF in parentheses. So yes, it has higher molar mass, and we're comparing within a chemical class. And it has a higher boiling point, though, specifically because it has stronger intermolecular forces. And these two things are tied together when we're comparing within a class of chemicals. Questions about that? So that's our dispersion forces. It's our first force. Our second force is the dipole-dipole force. What is a dipole? Does anyone remember what a dipole is? What does di mean? Two. Di means two. What's a pole? What's a pole in the context of a magnet? What's one of the poles on a magnet? The positive or north and the negative or south. So dipole we should be thinking about positive, negative. And it's a dipole-dipole force because this is a force between a dipole and another dipole. So all we're describing here is basically a little magnet force. Dipoles are permanent. Positive and negative. Partial positive, partial negative forces. So our dipole-dipole force exists in all polar molecules. So the dispersion force exists in everything that has electrons. The dipole-dipole force exists in everything that can be described as polar. So we need to be able to identify something as polar in order to be able to say that it has dipole-dipole forces. So polar molecules have permanent dipoles. This is what we mean by dipole in the name, dipole-dipole. We mean a permanent dipole because dispersion forces exist because of temporary dipoles, instantaneous transient dipoles. So just like magnets, the dipole-dipole force is an attractive between a positive end or a north end and the negative end or south end of a magnet. So all of our molecules have dispersion forces. Everything has dispersion forces. Polar molecules also, keyword here, also have dipole-dipole forces. Another note about this being our second force, it's stronger than dispersion forces. or stronger than the dispersion force. So one of the notable characteristics of the dispersion force, or the London force, or the London dispersion force, one of the notable characteristics of the dispersion force is that it's instantaneous. It's very temporary. I don't know what percentage of the time it exists, but even if it's 50%, that's not all that much time, and I would guess that it's probably less than 50%. Our dipole-dipole force is the result of permanent dipoles. So we don't have it just part of the time, it's always there. So polar molecules generally have higher melting and boiling points relative to nonpolar molecules of similar molar mass. So we're thinking of boiling point and melting point. The higher the number is, the stronger the forces are. Melting point and boiling point being BP. So higher boiling point and melting point means stronger intermolecular forces. If we're comparing things that are similar molar mass. If we're not comparing things that are similar molar mass, then it might not be quite as true. So here's what the dipole-dipole force looks like. We're looking at formaldehyde here. So this is the Lewis structure. It's got some lone pairs that were omitted. And then this is the space-filling model over here on the left. And the reason that this is a polar molecule is because oxygen has a higher electronegativity value than carbon, and so it pulls those electrons towards itself. And the hydrogens can't compete with the strength of the oxygen. If anything, I think they're also contributing a little bit. Carbon has a higher intermolecular force or electronegativity number. It's 2.5 versus hydrogens, which have 2.1. So if anything, they're contributing to this overall trend. So because of these electrons getting pulled over to the oxygen, we get a partial negative on the oxygen and a partial positive away from the oxygen, somewhere in this area, kind of between the hydrogen bonds. And this is a permanent force. It's always there. Because we have a permanent force, these formaldehyde molecules can stack up positive end to negative end. And these little dashed lines indicate there's an attractive force going on there. Any questions about what's going on in that slide? So again, it's because this is polar that we can say that it has dipole-dipole forces. So now let's look at the effect of polarity, being polar or being nonpolar. See how that affects melting and boiling point. So we've got a bunch of characteristics labeled here on the top. We've got the chemical formaldehyde and the chemical ethane. Formaldehyde is polar. That's the one we were looking at on the previous slide. Ethane is a hydrocarbon. Hydrocarbons are nonpolar. So we're looking at something that's polar and something that's nonpolar. They have similar molar masses. So we would expect dispersion forces to be similar. Or the dispersion force strength to be similar. However, again, one of them's polar, one of them's nonpolar. So the nonpolar one has one force. It only has the dispersion force. The formaldehyde, on the other hand, also has dispersion forces. It has electrons, so it can have dispersion forces. And because it's polar, it has dipole-dipole force. And when we look at the boiling point and the melting point, a higher boiling point or melting point means stronger forces. And formaldehyde has much higher boiling point and melting point compared to ethane. We're looking at negative numbers, so the smaller negative number means higher number. So we've got a difference of, this is about 70. And we've got a difference of about 80. It's actually exactly 80. Between the boiling point and the melting points, respectively. So the difference between these two is the same as the difference between about room temperature, or a warm day around here, and the boiling point of water. That's the sort of difference in boiling point and melting point gained by just adding the dispersion, or sorry, the dipole-dipole force. So it's a massive increase in the attractiveness and the stickiness of these molecules, of these compounds. The polarity, polar or nonpolar, also affects miscibility. Miscibility we've described previously. It can be crudely thought of as mixability, if miscibility is a confusing name, understandable. So are they mixable or are they not mixable? Can you combine them to form a homogeneous solution where you've got the same consistency throughout? Or are they going to be heterogeneous and form two separate layers? Generally, the rule is like dissolves like. So polar liquids are generally miscible or mixable with other polar liquids. But they're miscible, not mixable with nonpolar liquids. So the phrase like dissolves like, very common in chemistry, applies to this. So polar dissolves polar, generally. Nonpolar dissolves nonpolar. That's what we mean by like dissolves like. The reason that like dissolves like is helpful is that in a chemistry context, especially in a lab setting, you'll often know what chemicals are maybe in a mixture or you're trying to produce or dissolve. Like if you want to do an analysis of a chemical, you'll know what the chemical is, and with chemistry knowledge that you'll have gained over the years, you'll be able to make some predictions based on its shape about is it going to be polar or is it generally going to be nonpolar. And you can pick a polar or nonpolar solvent to dissolve it. Especially important if you just have no clue what it will dissolve into. There's a range, but generally, like dissolves like is the phrase that we would use. So for example, chloroform and water don't mix. We saw that in was our first lab or our second lab? Anyway, we saw that 4 weeks ago. Chloroform and water don't mix. They'll separate out into two layers, chloroform being more dense than water. Oil and water also don't mix. Oil is nonpolar, just like chloroform is, and water is polar, so those don't mix. And then this image on the bottom right is the Deepwater Horizon oil spill that was 2013. Feels like forever ago. And you can see kind of the shiny oil slick on the Mississippi Delta that was caused by all that oil spill. All the oil sitting up on the surface of the water. All right. So to determine whether a molecule is polar, whether it has access to dipole-dipole forces, there are methods. And we talked about the Book's method. I don't know if this is our current Book's method or if this is just the old Book's method. I don't remember. You need to figure out whether there's polar bonds. Has to have polar bonds to be a polar molecule. And then determine whether those bonds add together to form a net dipole moment. There's also the nonpolar express. So a molecule will be nonpolar if both of these conditions are true. Again, it has to be both of them. We have no lone pairs on the central atom, and the atoms bonded to the central atom are identical or have the same electronegativity, plus or minus a little bit. If either of those two things is not true, then it will generally be polar. So nonpolar if both true, polar if either/both, false. Again, with the important condition of having a polar bond. All right, determine whether each of these molecules has dipole-dipole forces. We have CF4, carbon tetrafluoride, sorry. We have CH3Br, methyl bromide. And we've got HCl, hydrochloric acid. And I'll give you a little bit of time to figure those out. All right, if you're still working on or got stuck on the Lewis structures, I'll just go ahead and draw them out for you. So CF4 look like this, lots of lone pairs. CH3Br, not as many lone pairs. And HCl, just like that. So now you can refer to your yellow sheet and the nonpolar express, or whatever method you choose, and figure out if these molecules are polar or nonpolar. All right, the first thing that we want to check for each of these molecules, do we have a polar bond? So we'll look at, I should have pulled my yellow sheet out. We'll look at the electronegativity values. I just don't know what bromines is for each of these and come to a decision. Do we have polar bonds or not? CF4, we definitely have a polar bond because we've got fluorine bonded to carbon. The carbon's got a 2.5, fluorine has the maximum value of 4.0. Our difference in electronegativity is 1.5. That's firmly within the realm of a polar bond. It's between 0.4 and 2. That's kind of where our polar bonds generally fall. So we've got a polar bond. Now we have to go through our checklist, our nonpolar express checklist. And I'm going to move that out of the way. Okay, so our two conditions. The first condition's what? Who remembers? Yeah, lone pairs on the central atom. So nonpolar express. No limited play, sorry, lone pair. No lone pairs on central atom. Is that true for CF4? Yes, that's true. There's no lone pairs on the central atom. There's tons of lone pairs, but none on carbon. So this is true. The second condition, all bonds equal or similar strength. Is this true? Carbons bonded to fluorine, carbons bonded to fluorine, carbons bonded to fluorine, and carbons bonded to fluorine. So 4 bonds, but they're all exactly the same. Since both are true, CF4 is nonpolar. Does it have dipole-dipole forces? The correct answer is, for those of you that are listening in on the recording, I was shaking my head, no. It's nonpolar, so no dipole-dipole forces. Dr. Pepper forces. I guess DD forces would just be fine too. Does it have any forces? CF4? We stay being interactive. Love it. It still has dispersion forces. Why does it have dispersion forces, or the dispersion force? Are all of the students in the class alive? Yes. All the students in the class are alive. I don't know what that was. Hopefully it wasn't a student not in the class. All the students in the class are alive because all the students in the class, I mean, there's lots of reasons to say you're alive, but you're all breathing. That would be one of the conditions for being alive, is that you're breathing. CF4 has dispersion forces because everything has dispersion forces. So that's how we know that it has dispersion forces. All right. What about CH3? CH3, we can go through our nonpolar express checklist. No lone pairs on the central atom. This is true. Okay, lone pairs. Check. No lone pairs. I'll write no in front of there to make it clear. All bonds equal? Are all bonds equal? No, all bonds are not equal because we've got carbon bonded to bromine. Bromine has a value of 2.8. Carbon's 2.5. Hydrogen is 2.1. So despite not really having a polar bond, like the carbon to hydrogen bond might be polar, but it's really on the edge, all of these forces would add up because bromine is the most electronegative, carbon's the most electronegative. So you get a little arrow this way, and we get little arrows this way, and then we get to think about it existing in 3D space. So we've got the bromine, that would be this hand up here, and then the arrows are all pointing kind of towards the bromine. So the hydrogens don't quite cancel each other out completely, so we'd have a big pull towards the bromine. So we'd expect a little bit of a negative charge towards the bromine side of things. So we'll say that this is polar. Does it have dipole-dipole forces, though? The answer is yes. It's polar, so it has dipole-dipole forces. Does it have dispersion forces? Yes, it has dispersion forces. The dispersion force is the less influential force. So it doesn't really make a difference that it has dispersion forces because everything has it. The dipole-dipole force is its major or leading force. All right, our last one, HCl. We've just got two things. So all we need to do is check if we've got a polar bond. There's nothing that could possibly cancel it out. So we've got Cl with a value of 3.0, hydrogen with a value of 2.1. Our difference in electronegativity is 0.9, which is firmly within the realm of being polar. Polar bond, so polar molecule. And our little arrow would be pointing towards the chlorine with the positive side being on the hydrogen. So partial positive, partial negative. Does it have dipole-dipole forces? People nodding yes. Why? Because all polar molecules have London dipole-dipole forces. I woke up early today, so my brain's a little mushy. All right, so it has dipole-dipole forces, and it exists, so it has dispersion forces. So those are our first two types of forces. Our third force is hydrogen bonding. So the first three forces we can kind of think of as a pyramid or like concentric circles, I guess would be better than a pyramid. Everything has dispersion. Some things have dipole-dipole. And some of those things have hydrogen bonding. So I think concentric circles would be better. Everything has dispersion forces. Some of those things that are included in everything are polar molecules. They have dipole-dipole forces. Some of those polar molecules, a subset of polar molecules, have hydrogen bonding as a force as well. So polar molecules that contain hydrogen atoms bonded directly to fluorine, oxygen, or nitrogen exhibit what we call hydrogen bonding. So our options are hydrogen bonded to fluorine, hydrogen bonded to oxygen, which is probably bonded to something else, and hydrogen bonded to nitrogen, which might be bonded to one or two things. So if that feature shows up in a polar molecule, then we would consider it to have hydrogen bonding. Hydrogen bonding is sort of just super dipole-dipole forces. So it's dipole-dipole forces, but it's extra powerful. So it's sort of a third force, but it's also kind of just more on the second force. It's a specific case of the second force, our dipole-dipole force. So if we look at fluorine, oxygen, and nitrogen, if you look at them on your periodic table, if you have your yellow sheet out especially, notice that fluorine, oxygen, and nitrogen are all in row 2. How does atomic size change as we move down the periodic table? As we move down, we're adding layers, things are getting bigger. So since they're in the second row, fluorine, oxygen, nitrogen are small. Row 2, so they are small. Right, so they're small. And they've got high electronegativity values. Fluorine has 4, oxygen has 3.5, nitrogen 3.0, and hydrogen's a 2.1 by comparison. So because they're small, they can get really close together because they're smaller. You can pack more small people in small spaces, right, than big people. That's why small people often get the back middle seat, unless you just have like a weirdo in your group. I've got a weirdo in my friend group who loves to sit in the middle. What a weirdo. He's also on the smaller side of the friend group, so it works out. Anyway, they're smaller, so you can pack them tightly together, so they get closer, and they've got a big electronegativity difference. And so it ends up being a super dipole-dipole force. It's stronger than normal or other dipole-dipole forces. Again, need to emphasize here, this is hydrogen atoms, but bonded directly to fluorine, oxygen, or nitrogen. This is not just, there's a hydrogen in there, so it has hydrogen bonding. It's only if it's these specific pairings. Hydrogen bonds are an intermolecular force because of that strong positive negative that's formed. They're not covalent bonds. So hydrogen bonding is a force that exists between molecules. They are much weaker than covalent bonds. They're like 2 to 5% the strength of a typical covalent bond. So they're much weaker than a covalent bond. They are relatively strong for intermolecular forces. So 2 to 5% compared to a covalent bond makes them seem really weak. And they are, in the grand scheme of things, they are weak. But this is really strong compared to dispersion and dipole-dipole forces. Hydrogen bonding is by far our strongest force so far. So let's look at HF, hydrofluoric acid. In HF, the hydrogen on each molecule is strongly attracted to the fluorine on its neighbor. So we've got a bond between hydrogen and fluorine using a space-filling model. So the size of the sphere, that's like the electron cloud. They're kind of overlapping here in the middle. And if they were being shared evenly, these electrons would be right on this line. They are not being shared evenly. Fluorine is the bully of electronegativity. It's got a value of 4 for its electronegativity, and so it's going to be pulling those electrons much closer to itself, in addition to having some other lone pairs in here. Because it's not shared evenly, we get this partial negative charge. There's extra electron density around our fluorine, so it's a little bit more negative than usual. And usually if you've got one molecule or one compound of something, you've got another one around. That's the case here. So because our hydrogen has a partial positive charge, it's attracted to the partial negative charge of the fluorine that's next to it. And so HF will kind of line up, the molecules will kind of line up this way if you get them all together. Just like a bunch of little magnets. And this attraction that we're looking at, that dashed line, this is Sparta? No, a hydrogen bond. So that's what we're talking about when we're talking about a hydrogen bond. We're talking about hydrogen bonding as a force in general. Questions about our first three forces? All right, methanol, wood grain alcohol. This is the alcohol that you can't drink. It'll make you blind if you drink it. Don't drink it. Methanol contains hydrogen atoms directly bonded to oxygen. That means that it has hydrogen bonding. So this red dot, the red bit here, that's our oxygen. The white bit, which I can't write in white because then you wouldn't be able to see it. All right, these are hydrogens. And then the black one here, this is the carbon. All right, so we've got, in this space-filling model, we've got oxygen directly bonded to hydrogen. That's our condition for hydrogen bonding. And so it can hydrogen bond to a neighbor. The hydrogen gets a partial positive charge. That's always the case in hydrogen bonding molecules. And then the oxygen, in this case, gets a partial negative charge. And so they can kind of link together because of that. So that's the hydrogen bond. And again, this is really strong for an intermolecular force. It's weaker than our covalent bonds, the ones that exist in the molecules, but it's really strong for an intermolecular force. And we'll look at what that strength is here. So now we're comparing the effect of hydrogen bonding. We've got methanol, we just saw that. Polar and has hydrogen bonding. So we had previously looked at something that was polar but didn't have hydrogen bonding. And we're comparing that with ethane, which is nonpolar. So this has dispersion forces only. Methanol's a bit of an avatar here. Has all three forces. And we are comparing with similar molar mass, so we would expect the dispersion force to be similar. So this lets us compare kind of more directly. If the baseline of dispersion forces is about the same, then any differences are going to be due to methanol having the other two forces, hydrogen bonding being the strongest of the two. Earlier, when we looked at this, previously it was about 70 degrees Celsius for a difference in boiling point, and for melting point, it was 80 degrees. And the difference that we have now is minus 88 to about 65. So that would be a lot. 140. About 140 degrees Celsius. So this is bigger than the difference from freezing water to boiling water. So you could take an ice cube and turn it into steam, and that's about the difference in the boiling point change. And then the melting point is a little bit bigger than, it's like 85. Don't check me on that. It's in that realm. So much bigger boiling point difference and still a bigger melting point difference, just not quite as big. So because of the increased boiling point and melting point, that means it takes more energy for them to switch from being a solid, where they're stuck in place, all the molecules are stuck in place, they can't move past their neighbors. It takes more energy for them to get from that state to being able to move past their neighbors, that's our melting point. And for our boiling point, it takes way, way more energy, 140 degrees Celsius temperature, to go from being able to move past their neighbor to being completely separated. So they're much, much stickier. You have to pour a lot more energy in there to get the molecules to vibrate around a lot more for them to finally separate. Water is an especially odd case of extremely high boiling point and melting point for how small it is. Part of the reason, well, the big reason for this, we've got oxygen directly bonded to hydrogen twice. Right, so all we've got lots and lots of hydrogen bonding. Can double hydrogen bond, basically. And so water will stack up this way. This is part of the reason that you get nice ice crystals, because it stacks up this way. So the boiling point of water at 100 degrees Celsius is higher than the boiling point of methanol, which is bigger. It's got a molar mass of 32, and its boiling point is below that of water, and water is a smaller molecule. So it's really outstanding how high the boiling point of water is. Hydrogen is also responsible for keeping your DNA together. So this is part of the reason that we exist, that a lot of life exists, because DNA double helixes are held together by hydrogen bonds between your different base pairs, which of course you don't need to know the base pairs. At worst, I'll test you what force is responsible for DNA being held together, but I don't think I've done that in the past. This is kind of just shout out to biology here. All right, which of these two has the higher boiling point, HF or HCl? And why? What will cause a higher boiling point? What causes boiling point to be higher or lower? What are we thinking about here? Is it the value of the dollar against other currencies? Is it who gets how much money and where? It's not either of those things. It's intermolecular forces. How sticky the molecules are to each other. What kind of intermolecular forces? Stronger intermolecular forces. Stronger intermolecular forces result in a higher boiling point, a higher melting point. So which of these two has the stronger intermolecular forces is really what the question is. Let's think about what forces we have. What force does everything have? Everything has a plumbus? No, dispersion forces. So both dispersion forces. What other forces do they have? What's our next force? Dipole-dipole forces. They both have dipole-dipole forces as well. What's our strongest force so far? Hydrogen bonding. Does one of these have hydrogen bonding? Yes. HF also has hydrogen bonding. because it also has hydrogen bonding, despite it being the smaller molecule, it has stronger intermolecular forces. It has a higher boiling point. Questions about that? So those questions I was asking, the steps of what do they have in terms of forces? What causes higher boiling point? Those are some of the steps that you should hopefully try to work on thinking about to make these sort of comparisons. That's what I would recommend, is kind of think through what's going to cause higher boiling point. Well, stronger intermolecular forces are going to cause higher boiling point. Which one of these has stronger intermolecular forces? Let's tally up the forces that they have. And so HF is going to be the winner here for higher boiling point, despite being smaller. Part of the reason that we learn about intermolecular forces is that we can make some predictions about the state of matter. So the physical state of any bit of matter depends on strength of intermolecular forces relative to the amount of thermal energy. So basically intermolecular forces versus temperature. Every atom, all atoms, including those that are bonded, are in constant random motion. And that increases with temperature. So atoms move/vibrate faster as temperature increases. Things that have weak intermolecular forces, like just dispersion forces, are relatively weak to stick together. They're not very sticky. They're more likely to be gases. If the intermolecular forces are strong relative to the thermal energy, things that have dipole-dipole or hydrogen bonding, those are more likely to be a liquid or a solid. Things that are more stuck together than gases. So we've got categories. I think we've talked about some of these categories a little bit. We've talked about crystalline solids. I don't think we talked about subcategories of crystalline solids. So crystalline solids or amorphous solids, those are your two options. So we've got things with long-range repeating order, things that form crystals. Crystals are just you seeing that long-range repeating order, but like on a really big scale relative to the atoms and molecules. So like our alum that we made in lab that's hopefully crystallizing. That's a solid that's crystalline. Crystalline solids can be divided into a couple of categories based on their individual units. We've got molecular crystalline solids. Any guesses about what sort of compounds make up molecular crystalline solids? It's the great Greek hero, molecules. Ionic crystalline solids are another category. Any guesses on what sort of things make up ionic solids? Yep, that's right. It's ionic compounds. Ionic compounds being comprised of a metal and a nonmetal, or more generally a cation and anion. And then we've got atomic crystalline solids. What makes up an atomic crystalline solid? Any guesses? Somebody's got to know. Look at the trend. Is it the first man? according to a particular story? No, it's, well, yes, but no. Atoms. So the naming is not complicated, right? Just figure out what kind of thing it is. Is it a molecule, all nonmetals? Is it ionic, metal and nonmetal, or is it just an atom? You can figure out what type of crystalline solid you've got. So molecular solids, again, no surprise here, solids whose composite units, its smallest units, are the Greek hero molecules. Examples being like ice or dry ice. So two types of ice. There's more than two types of ice. There's like 20 types of ice. Most of them don't exist right now. That's specifically talking about water ice, and that's just where my brain's going today. So solid H2O or solid CO2, two types of molecular solids. Molecular solids are held together by intermolecular forces. And intermolecular forces include the three that we've learned: dispersion forces, dipole-dipole forces, and hydrogen bonding. Ice is held together by hydrogen bonds. That's water ice, wet ice, held together by hydrogen bonds. Dry ice, CO2, is held together by dispersion forces, because CO2 is nonpolar. Relative to all things that exist in all temperatures, these tend to have low to moderately low melting points. Ice has a relatively high melting point. Of 0 degrees Celsius, which is not very high. There are other molecular solids that have higher melting points that might get into the hundreds or 200s of degrees Celsius. But generally, molecular solids are going to have low melting points. Ionic solids are, surprise, surprise, composed of formula units. They're ionic, so they've got ions. These are held together by electrostatic interactions between cations and anions, which, as a reminder, positive and negative charged ions. In our molecular solids, let's say that we've got something like ice. We've got dipoles in ice. Are the dipoles partial positive and negative, or complete positive and negative?
Positive and negative.
Are they partial or complete?
Partial.
Partial. So these are partial plus minus for things that have dipoles. Not everything has dipoles. In ionic solids, these are full positive negative. Right? So we were looking at partial positive negative. That's going to be relatively weak because it's just a little bit of plus or minus. Ionic bonds, we've got full plus minus. And because we've got full plus minus, we can think of these as being really strong magnets compared to our relatively weak magnets of the molecular solids. And these are going to tend to have high melting points because of the high bond strength. Because of those full plus minus charges. So where water had a melting point, has a melting point of 0 degrees Celsius, table salt, sodium chloride, has a melting point of 800 degrees Celsius, which I would consider to be high. Your oven at home maybe goes up to 500 degrees Celsius. You would need another 300 degrees Celsius on top of that to be able to melt sodium chloride. So this is way higher than water. And I mentioned there were some other molecular solids that can also have really high melting points of like kind of the hundreds to 200s range. Those do exist, but sodium chloride beats those by a lot, 800 degrees Celsius. So ionic solids tend to have high melting points. Atomic solids are made up of individual atoms, and we can break that down into further groups. So we've got three groups of atomic solids. So our umbrella, we've got crystalline solids. That separates out into molecular, ionic, atomic. Atomic breaks into further subcategories that we're going to talk about here. So we've got covalent atomic solids. Covalent atomic solids are held together by covalent bonds. Our example here, diamond, graphite would be another example. There's probably some other things. All that I can think of is stuff that's made of carbon. A diamond is just, assuming there's no inclusions, just pure carbon. It's essentially a really, really large molecule, and the melting points are even higher than what we saw for ionic solids. So diamond has an estimated melting point of 3,800 degrees Celsius. This is super high. Like, I can't even imagine what would be in the realm of 3,800 degrees Celsius. I think that, like, I'm pretty sure that's well above the melting point of, like, metals. All metals. So that's a lot higher than 800 degrees Celsius. So that's covalent atomic solids. Covalent bonds are really strong. And that's why we've got really high melting points. So here's a diamond in the rough, and then the crystal structure of diamond. The purple bits here are just representing corners of a unit. So you would just repeat this unit over and over again, connecting them for a diamond. Not really that important, just kind of fun to see it. Then we've got non-bonding atomic solids, things that are held together by very weak dispersion forces. So things like our noble gases, for example, which are not going to bond. Noble gases don't bond, and so we only have dispersion forces. Xenon has a relatively high melting point for a noble gas at negative 112 degrees Celsius. Remember, helium boils at 4 Kelvin. Not that it's really that important, but it's an impressively low number. Imagine being caught boiling in 4K. Couldn't be me. And then we've also got metallic atomic solids, which are made up of metal atoms. And since this is just made up of metal atoms, one way we think of them is there are a bunch of positive charges, and then they just kind of freely share their electrons between them. That's why they conduct electricity so well. So an example would be iron or mercury. So thinking of any of the metals on the periodic table, there's many to choose from. These tend to have very variable melting points. For example, mercury is a liquid at room temperature, but iron melts. The number I've got here is above, or at, sorry, 1800 degrees Celsius. So there's a big range. It can be a liquid at room temperature, mercury. There's some other ones that melt at relatively low temperatures. I'm trying to remember. I know gallium. Gallium would probably be the best example. Gallium will like melt in warm water. So you can buy like fake spoons. It's made of gallium, and then you give it to your friend, and they like stir their tea or whatever, because we're fancy and we stir our tea in this example. And then like they're like, oh no, what happened to your spoon? It's melted. It's gone. A fun one-time prank that you can do on somebody and hope they don't drink it. So a variable range for our metallic atomic solids. This is what those metallic atomic solids might look like. We've got a bunch of positively charged nuclei. That's like the atoms of our metals, and then they're sharing their electrons. So the electrons can just kind of go wherever they want to. All right, identify each of these solids as molecular, ionic, or atomic. What kind of compound is NH3? Yep, that's right. It's a molecule. Somebody was thinking it somewhere. NH3 is a molecule, and so it's going to be a molecular solid. How about the ever-important statistic, runs batted in? What kind of solid is RBI? Yeah, it's an ionic compound. Since it's ionic, it's going to be, surprise, surprise, an ionic solid. And Kr. Krypton, molecular, ionic, atomic. Again, somebody was probably thinking it's atomic. What kind of atomic solid is it? Or would it be? Is it covalent, non-bonding, metallic? What group is it in? It's non-bonding. Because it's a noble gas. Questions about any of those? How we got any of those answers? Kind of digging up old ideas. Have we talked about properties of liquids and solids? I think we have, so we'll just go through them quickly. In gases, as stated in our kinetic molecular theory, our molecules and atoms are separated by large distances. There's empty space in between the molecules. They're not touchingly close. In our solids and liquids, the molecules or atoms are touchingly close. They're right next to each other. They're interacting directly with each other. The difference between solids and liquids is in their freedom of movement. So can they move past each other, or are they stuck in place? In our liquids, the atoms or molecules are free to move around each other. They're always going to be touchingly close, but they can get past each other. They can do fun little hand movements like I'm doing now. And in solids, the molecule or the atoms are fixed in their positions. Can't move past each other, can't move around each other. Can't move around each other. However, that doesn't mean that they're not moving. They are still moving, just like people in a movie theater, even if they have assigned seats, are still moving. You're drinking your popcorn, you're eating your soda, et cetera, et cetera. And here's a visual of what that might look like with oxygen. So in our solid state, they're touchingly close, and they're all lined up. I don't know that they necessarily have to be all lined up, but looking at that to show an example of them being crystalline, perhaps. For O2 as a liquid, it's still very close to each other, touchingly close. They can interact with the neighbors, but they can move past each other and they can rotate in their place. And for O2 as a gas, there's whole big swaths of empty space in there. Properties of gases. Gases have very low densities in comparison to our liquids and solids. They have an indefinite shape. They have an indefinite volume. So you can compress them. You can expand them. They'll take whatever the shape of their container is. They've got very weak intermolecular forces relative to thermal energy. They're not stuck together. Right, they're completely separated. If they ran into each other and stuck together, that would be condensing. Then they must have relatively strong intermolecular forces. These, not even sticking to each other, they just bounce off. Not stuck together, weak forces. Liquids have high density compared to gases. They also have indefinite shape, but they have definite volume. So you can't compress a liquid, which has all sorts of useful properties. These have moderate intermolecular forces relative to thermal energy. So they're sticky enough, they have strong enough intermolecular forces that they can't escape their neighbor, but they can move past their neighbors, they can move around their neighbors, they can mix and mingle. So they don't have enough energy to separate out and be completely free. So stuck to nearby units, but free to move, but can move around them. So touchingly close, but not stuck in place. Solids also have high densities compared to gases. These have definite shape, which is great. They have definite volume as well, and they are either crystalline or amorphous. They have long-range repeating order. They can be any of our crystalline solids that we talked about previously. And these have strong intermolecular forces relative to the thermal energy. So they're stuck together and stuck in place. And the reason that we're reviewing these properties, and I'm going to skip some of this stuff, is because we're going to talk about phase changes a little bit. So without intermolecular forces, our solids and our liquids wouldn't exist. If everything was just dispersion forces, none of the molecules, the atoms, would stick together, and so we wouldn't be able to exist. Our tables wouldn't be here, our chairs wouldn't be here, we wouldn't be here, our water wouldn't be here. It would all be gas, it would all be vapor. And there's some other properties that arise because of intermolecular forces. So surface tension is one of them. This is something you could try at home, just don't drink it. You can actually set things like pins and needles or little pieces of metal or paper or other things on the surface of water, and they'll just float there. Even though a paperclip will definitely sink in water, if you set it down gently enough, it will just sit on the surface of the water. The reason that it'll do that is because of surface tension. So surface tension is a result of intermolecular forces. And one description or one definition for it is the tendency of liquids to minimize their surface area. This is also the reason that water droplets exist, as I think we'll see. If you try to do this on gasoline, don't try to do it on gasoline because you'd be smelling too much of that delicious, beautiful gasoline smell. And it's also really flammable, so don't do it. But if you try it on gasoline, it's not going to work. The paperclip will just go right into the gasoline because of the weaker intermolecular forces. Surface tension, also the reason that mosquitoes and other insects can stand on water. Hate mosquitoes. Again, it's because of surface tension. So surface tension, we're looking at the forces in between these different water molecules. We're representing our water molecules as these blue spheres. So anything that's on the inside is going to be pulled every which way, all directions, 3 dimensions. And so that's going to overall cancel out because you're being pulled in every direction. If you're on the surface of the water, though, those molecules are not being pulled every which way, right? They're only being pulled next to them and down. They're not being pulled up. And so what you have is like a net compression force. The surface of the water is being pulled down and inward a little bit. So surface molecules experience a net pull in. And because you're kind of sucking in the surface of the water or whatever the liquid is, that magically produces this surface tension effect. You could sort of think of it like a little bit of a rind on the water. And this is the reason that water drops are spherical, is because of that tension force. All of the water molecules want to pull in, and the best shape for that is in a sphere. So that's why we can get these pretty pictures of water drops. And we've got this very fun picture on a space shuttle where there's very little gravity or no gravity. And so you can have large spheres of water floating in the air. And this, I imagine, is a relatively dangerous picture to have taken because somebody accidentally sneezes, that water is going everywhere. And you definitely don't want that. This is also the reason that they have like those fun toilets on the space shuttle. So you can get really cool pictures like that up on the space shuttle. One of the other things that comes out of intermolecular forces is viscosity. Viscosity is the resistance of a liquid to flow. And high viscosity means low flow. Low or slow. Flow. So things like motor oil is more viscous than gasoline. So think about nonpolar liquids. Honey is more viscous than water. Low viscosity will be high flow or fast flow. Surface tension is also the reason that you can like overfill a drink. You've probably overfilled a water bottle or a glass before, where you fill it up all the way and then you can fill it up a little bit more, and there's kind of water sticking up above the surface of your cup or your whatever you're doing, right? That's also because of surface tension. If you break that tension with some soap or something, then it should spill out, and then you've also soaped your water, and now it's no longer safe to consume. So don't do that. Another way you can think of viscosity is that this is like the thickness of a liquid. So higher viscosity, thicker liquid. Viscosity is going to be greater in substances with strong intermolecular forces, and that's because the molecules can't move around each other as freely. So they're a little bit more stuck to their neighbors. So it's a little bit harder for them to slip past their neighbor, so it's going to slow more slowly. Honey being an example of this, there's a lot of sugar and other things dissolved in there, and those forces kind of gum up the works for the flowing action. The flowing action is the molecules moving past each other, and if you've got a bunch of strong forces in there, then it's going to slow down the rate that they can flow. So it would be an example of high viscosity. Some of our phase changes: melting, freezing, and sublimation. as you increase the temperature of a solid, your thermal energy gets those molecules moving faster and faster. And once you get to the melting point, those atoms and molecules can turn into a liquid. They suddenly have enough energy that they can break away from some of their neighbors. They can't completely separate. They can break away some of their neighbors and slip past and turn into a liquid. So melting, when ice melts, you break free from that solid structure and they can now move past each other. One fun thing about melting is that if you have ice and water both present, solid water, liquid water, the temperature will be, at least at room atmosphere, 0 degrees Celsius. Locked in, always 0 degrees Celsius, never going to be lower, never going to be higher, always 0 degrees Celsius. Which means that ice water drinkers have a very consistent experience. If you've got ice in your water and it's well shaken, 0 degrees Celsius every single time. If you don't have ice in there, who knows? It's the Wild West. You live for adventure. Only after the ice has melted will the temperature get above 0 degrees Celsius. This is, of course, assuming that it's well shaken. You can have little areas of your drink that are warmer. Which is important. Sublimation is a phase change. This is solid to gas. All solids, to a very small extent at least, will turn directly into a gas. The most notable example of sublimation is dry ice or solid CO2. So carbon dioxide, you can buy it at not every grocery store, but some grocery stores will sell you dry ice if you're 18, is solid carbon dioxide. It never turns into a liquid at normal atmospheric pressure. So it goes directly from that solid state, locked in place, not moving past your neighbor, goes directly from that into being completely separated. And it does that at the low, low temperature of negative 78 degrees Celsius. Very cool. And so you can do fun stuff, like you can get this vapory look. So you put some dry ice into a bowl and it like bubbles and stuff. And there's other fun things you can do, like you can carbonate beverages. Somebody should try it with milk and let me know how bad it tastes. You just put a little bit of dry ice in, it melts, and then some of that will dissolve into the solution. Don't do it in a glass jar because the glass will probably explode, and that's bad for your safety. But if you do it in a plastic bottle, it'll also probably explode if you put too much in, but it's less dangerous for your safety. So yeah, it goes directly from solid carbon dioxide to the gas form of carbon dioxide. There's no liquid carbon dioxide at normal atmospheric pressure. Regular ice, like wet ice, water ice, also sublimes. It also sublimes even if it's below 0 degrees Celsius. So this is the reason that in cold places, the ice or snow will disappear over time, even if your temperature remains below 0 degrees Celsius. This is also the reason if you don't use your ice cubes, and especially if you've got like ice trays, if you leave them in there for long enough, they start to get real weird shaped. You'll notice they pull away from the sides of the container. They might shrink down. You're like, why do I have these tiny ice cubes? I haven't touched them. That's why. It's because you haven't used them. So ice cubes that are left in your freezer long enough, ice in the freezer sublimes. If you leave them in there long enough, they will become weird shaped. And I'm not talking about the ones that have like the weird like unicorn horn thing that sticks out of the top. That's a different thing. But like when they start to shrink and get funny, weird, jagged shapes. This is also the reason that you have to defrost your freezer, assuming you don't have an automatic defrost cycle built in, because ice from other places in your freezer will turn into gas molecules. It'll sublime a little bit, and it'll go and land on like the walls of your freezer, which is where it's the coldest usually. Ice will also sublime out of food. So if you put a bag of fruits or veggies or just anything in your freezer, all the water that's in that will also sublime out of the food, and then it'll form into crystals on the surface of the bag, or like on the lid of your ice cream, for example. Food that's frozen for too long becomes dried out. This is freezer burn. So the water that was inside of your food leaves, and it doesn't go back in. So if you leave stuff in the freezer for too long, then you can get freezer burn, where your food starts to lose its normal consistency, its taste. It doesn't rehydrate well. It doesn't cook well. If you take things to much colder temperatures, that would be deep freezing, and that will decrease the rate of sublimation, and so it will stay frozen longer. You probably don't have a deep freeze unless you specifically went out of your way to buy one, because you knew that you were going to be freezing things for a really long time. So colder temperatures lowers the rate of sublimation, preserves your food longer. The big takeaway, the practical takeaway I think here, is that you have to eat your ice cream before it goes bad. Because I don't know about you, but I've certainly had the experience of opening up my favorite ice cream, and I can see the ice on the lid, and I know it's doomed. That ice cream is not going to taste good, right? Don't let your ice cream go bad. Eat it before it gets freezer burn, because ice cream will also get freezer burn, and that can be very disappointing because it just doesn't taste the same. Some other phase changes. Boiling, evaporation, condensation. So evaporation and vaporization are two names for the same phase change. That's moving from a liquid to a gas. Rate of vaporization, rate of going from a liquid to a gas, changes. It's not always the same. It will increase with increasing surface area, increasing temperature, and decreasing strength of intermolecular forces. So spreading out the liquid increasing the surface area, increasing the places that it can evaporate. Evaporation is only going to take place at the surface. So if you spread out the liquid, you're going to get more places where the liquid can evaporate. If you increase the temperature, that's also going to increase the amount of energy that your molecules have, your particles have. So it'll be easier for them to break away from their neighbors. If you decrease the strength of the intermolecular forces, that'll also increase the rate of vaporization. So if you're working with things that are nonpolar liquids generally are going to tend to have lower intermolecular forces. So you'll get increased rates of vaporization. So think of gasoline or isopropyl alcohol. You can smell them, you can feel them evaporate quite quickly. Hopefully you haven't gotten gasoline on your skin. But if you get water on your skin, like it provides a slight cooling effect, versus acetone, which has much less intermolecular forces, feels really cold, or like hand sanitizer has weaker intermolecular forces compared to water, and that's why it feels so much colder. You're feeling the heat leave your hand as the liquid evaporates. So those are three things that change rate of vaporization. The arrows are important. We'll put a box around it too. Might as well. Liquids that evaporate easily are termed volatile. I think the reference point, at least in my head, the reference point is compared to water. So if it evaporates more easily than water, it's volatile. If it vaporizes less easily or less, then it's non-volatile. How many of you have watched a basketball game? Great. 2 people have watched a basketball game. You've probably seen in a basketball game, especially if you've been to a high school basketball game. Most of us, I assume, were in high school at one point. If you've been to a high school basketball game and you see somebody go up for a free throw and they fall down, I'm just kidding, it'd be a layup, and they fall down, and then presumably they're sweaty, and now there's sweat on the ground, and that's a hazard because somebody could slip and fall. banana peel effect, right? What do the basketball players do when somebody slips and falls? They pick up their teammate, unless they pick themselves up. And then what do they do to the area that they fell on? They all gather around and they kick the ground with their basketball shoes. Or if it's like a nicer school, then they'll bring out one of those brooms and just sweep it up. Why do they kick the ground? Is it to disrespect their fallen compatriot? It's not. It's because there's water on the ground. And if you increase the surface area and you increase the temperature, the rate of vaporization increases. So in order to get that water, that sweat, to dry up, you kick it. You kick the ground. That puts the water on your shoe, spreads it all over your shoe. It also causes a little bit of friction, which increases the temperature. Ergo, the sweat dries up in a hurry. So that's one practical application. The other, rate of vaporization increases with increasing surface area, increasing temperature. How many of you have used a blow dryer for your hands or a hand dryer for your hands? The ones that blow at you. Great. At least 4 people have used that very common bathroom appliance. How many of you have done that and then you're sitting there with your hands under the thing and you're like, when are they going to be dry? And you eventually just give up and you walk out and your hands are still wet? You don't have to do that. Because of science, because of this class, rate of vaporization increases with increasing surface area. If you rub your hands together, you can spread the water out on your hand, increases the surface area. That increases rate of vaporization, so it's going to dry out faster. Increasing temperature, you have no control over that. But if the air coming out is hot, that'll heat up the water faster. It'll dry out even faster. So unless you're using one of those like Dyson Airblade things where you just groovy your hands in it, right, and the water blows off in one direction, shout out One Direction, then rub your hands together and you will be amazed, you'll be shocked and amazed at how quickly your hands dry compared to just holding them there and waiting. So you never have to leave the bathroom with wet hands again unless you just choose to do that. You can't do anything about the strength of intermolecular forces though. Okay, so lots of stuff there that's not going to be on an exam, but is very practical to everyday life. What's happening in evaporation is this. So we're looking at a liquid and the gas. At the surface of the liquid, we already talked about how we're not being pulled in every which way. We're just being pulled sideways and down. Right? These liquid molecules are just being pulled sideways and down. So surface, not pulled in every direction. Because they're not being pulled in every direction, they're being held less tightly. There's less things pulling on them. And it's possible that through a random act of energy distribution, one of these surface molecules might get bumped twice at the same time by its neighboring molecules. And that gives it more energy than its neighbors, and it breaks the chains and it goes and becomes a gas. And that's what's happening in evaporation. These surface molecules are randomly getting bumped out. They've got more energy than holds them in by their neighbors, and so they can escape as a gas. When they do that, they take more than their fair share of the energy, and that's what causes the cooling effect of water evaporating. That's why sweat evaporation works. That's why it cools you down. And now here's one of my favorite graphs. Look at this graph. Sorry for anyone online on the video. So we've got energy on our x-axis. As we move left to right on the x-axis, we're looking at the amount of energy that these molecules have. And then the number of molecules is our y-axis. So a tall peak means a lot of molecules, and the further to the right we are, the higher the energy is. So that's what we're looking at here. And we've got 2 temperatures that we're comparing. We are comparing temperature 1, low temperature, and temperature 2, high temperature. So we've got at any temperature, there's a distribution of energy. A lot of the molecules are going to be one temperature. So if we're looking at this blue line, our low temperature, we've got a lot of molecules that have low energy, generally low energy. However, some that have low energy, and there's some that have relatively high energy. And it tapers off the higher the energy gets because overall the energy is relatively low. And this E that we're looking at here, this is the energy that's required to evaporate or to escape. Because we've got a small tail on our high energy side, some molecules are high energy. Because we've got that small tail, we can get a little bit of evaporation happening, even though we're at a relatively low temperature. If we increase the temperature, this whole thing shifts up. So this peak shifts up and flattens out. So overall, our energy is increased. And because our energy is increased overall, we now have a larger amount in that high energy tail on the right side. So we've got more molecules that have energy to escape or to evaporate. This is like happening on like a sliding scale. You can imagine this peak getting steeper and lower and getting flatter and further to the right as we increase temperature. This is for not being at boiling point. This is just like room temperature. So if we increase the temperature from T1 to T2, we get more molecules that are in this crucial can escape zone. And that's why increasing temperature increases the vapor pressure or vaporization. Condensation is the opposite process. It's going from gas to a liquid. So gas to liquid. There is a time and place where condensation and evaporation are equal. We call this a dynamic equilibrium. Equilibrium means that two things are equal. In this case, it's two things are equal. The dynamic part dynamic versus static. Static would be nothing's changing. Dynamic means that things are changing. Things are changing or moving. So a dynamic equilibrium describes a state in which we've got rates of evaporation and condensation. Those are the things that are equal. We still constantly have molecules going from the liquid state to the gas state and from the gas state to the liquid state. Because the rates are the same, the amounts don't change. So this is a very specific set of circumstances. Our vapor pressure, the vapor pressure of a liquid, is the partial pressure. We learned about partial pressure last class. The partial pressure of the vapor in dynamic equilibrium with its liquid. So partial pressure, but specifically when it's in dynamic equilibrium, when it's had time for it to get as much vaporization happening as it can. So vaporization no longer increases. We've got the constant back and forth now. You can witness dynamic equilibrium if you just leave like a water bottle out. Over time, your container of water will no longer keep evaporating more liquid. Like it'll keep going, but the amount that it condenses out will also match that. And so it won't lose any more water into the gas phase. And the vapor pressure describes the partial pressure when it's at that state, when it's in dynamic equilibrium. So vapor pressure requires dynamic equilibrium. And the reason that I'm stressing this so much, the dynamic equilibrium part. Vapor pressure increases with increasing temperature. So we're getting more of those molecules above that vaporization line. That's my favorite graph. Increasing temperature, we've got more things that can escape, and decreasing strength of intermolecular forces will also increase vapor pressure. The thing that's not on here that we saw on the previous thing that also had increasing temperature and decreasing intermolecular forces, the thing that's missing here is surface area. And the reason that surface area is missing here, because we're at dynamic equilibrium means that we've got the rate of evaporation and the rate of condensation are the same. And since we've got both of those things happening, surface area affects both of those, and so it ends up canceling it out. That's the whole reason that I talk about the dynamic equilibrium stuff and emphasize it here, is because it affects both evaporation and condensation. So increasing the surface area doesn't change anything. So if you've got a larger surface area, that's more places where you can evaporate from. It's also more places where you can condense. In lab 9, we're going to be using the vapor pressure from a table. And the reason that we can use vapor pressure without measuring the surface area is because the surface area affects vaporization and condensation equally. This is very helpful for us. It would be a huge pain to have to measure a cross-sectional area of a cylinder. That's not something that I would enjoy doing. It sounds very tedious and not fun. Any questions about the first half or so of this chapter? Apologies for no break, but we'll wrap up there.